beta decays. So now what we want to do is that we want to ask the same question that we did with alphas. I'm not really sure how I placed it or how I worded that question, but it's probably something like, how does a beta decay change in unstable nuclei? And you're going to see that this is more complicated. This is something that the vast majority of the people are, are going to be quite surprised with this thing here. So hopefully I surprise you, because I think this stuff is really badass, really badass. So once again, where do we start? We start with our band of stability, right? That's like our periodic table now. It's really important that we continue to stick to this, because this tells us what's going on. So the first thing that I would probably say here is that I want to sort of start listing these things. And what I want to do here, so the first thing here is that I want to give you an overall view of beta decays, because these are more complicated than alphas. So if I think about an overview of beta decays, we say here is that they come in two forms. Okay, there's beta and there's inverse beta. So guess what? Inverse beta is the turquoise region. So when I look at the table, this guy tells me it's the, God, I always spell turquoise wrong. So if I mix up two of the letters, just ignore it. And then the inverse beta is the orange region. So when I go and I look at this thing, you can see here is that when you look at the turquoise, look at that black line of stability. The vast majority of them, right? The vast majority of the turquoise region is above the black line on this table. And then you see that there's some that actually occur in the very, very heavy elements here. So this guy right here, this is the region of beta decays. And then if you look at the orange one, it's a little bit more complicated. You're seeing that the orange, that the vast majority of these guys are occurring below the black line of stability. And then you see that there's an isolated region up here. Okay, so in this region right here, this is what we call inverse beta decay. And it's very systematic how it works. It's not, something that, happens randomly. There's very good reasons why this graph is really what it shows here. And this is the view I want you to think. So a good way to view beta decays is to imagine of a valley. So what do I mean by a valley? So when I look at the graph, even though you visually, it's hard to kind of see here, you're finding here is that right here at the bottom of the valley, this region is the valley of stability. And all particles want to be in the valley of stability. By the way, this is also the black line of stability. And that's where all stable nuclei live. And so what you find here is that we could imagine that we have a valley. So then what we're going to say here, so if you're high up in the valley, this is where you have highly unstable nuclei. So if you're high up in the valley, you're very unstable. So if you have a rock, what's going to happen to the rock? Well, it's going to roll down. Why? Because it's in an unstable position. And so what you find here is that if you have an unstable, highly unstable particle, what does it do? It's decaying. And as it decays, what's it doing? It's always moving towards the black line of stability, the valley of stability. And it's this blue here, that's the area of the betas. And then if I look at the other side of the valley, it's a different process that actually happens, but you still have highly unstable particles. And as they decay, they continue to decay all the way down to the valley. And in this region here, that's the region of the inverse betas. And what you're seeing here is that I have a graph. I didn't come up with this. There was an Italian guy who won a Nobel Prize for his work in nuclear physics. And he's the one that actually came up with this picture, which is ingenious. And this is a modified picture, and it looks like this here. The unfortunate piece here is that it doesn't match the colors. They should have had these turquoise colors on the left and the orange colors on the right, but they don't. So we'll have to just stick with this. So now let's look at the valley. Down here, these are the stable heavy nuclei. So this right here is where you get the valley of stability, right? So right here is the valley of stability. So all nuclei want to move in that direction. So when you go and you look at the turquoise region, and beta is typically called beta minus, then you're seeing this is that turquoise region right in here. It starts all the way here and you're moving. And so you could see he called them drip lines. So particles are following these drip lines and they're very systematic in what actually happens here. And then on the other side, you have the inverse beta decay. So that means that particles are all sliding down along very specific paths. And then look at the very back with the mountains. That's the super heavy element. So in this case, this would be the alphas here. In this region, we have the alpha particles. So all the alpha decays are moving towards that. And so that's where my picture comes from. It was from this Italian guy, and for the life of me, I can't remember his name. That's horrible that I can't remember his name. So I'm going to make this a little bit smaller. By the way, just to let you know, this is shown. I put links to this image in the lecture notes. Okay, so now let's continue. So we started with the overview of what beta decays do. So they're high up on the walls of the valley and they're decaying down towards the valley of stability here. And I love this way of looking at it. I think it's very intuitive and they follow very specific processes. Okay, so now here we go. How much time do we have? Oh, no, we got plenty of time. I kept thinking that we were done at 10 till 9. Okay, here we go. Now we want to talk about what is a beta particle. So a beta particle, not beat. A beta particle is an electron. So when I look at a beta particle, it really is, right? That means here, if I have a beta particle, we call it beta minus, and this thing is an electron. And you might be asking, why didn't Rutherford call it an electron? It wasn't so easy. It was, he didn't know what it was. It's not that easy when you're, in the early days of experiment. Okay, so here's what we know. So in beta decays, a nucleus spontaneously, remember there's that magic that I'm talking about, decays by emitting a beta particle. That's what this beta decay does here. And here's where it's strange here, is that beta decays change a neutron into a proton. Literally alchemy. It's alchemy happening. And again, there's this magic. So what you're seeing here is that you start off with the neutron, and now it does a beta decay. And as it does this beta decay, it converts the neutron into a proton, which is amazing, right? It starts off blue and then suddenly it becomes red. It's like just magic. And now it emits the beta particle plus energy. And that energy is what we talked about before, where what you're seeing here is it's the emission of neutrinos. This is what a beta decay is right there. So this is why if you hold a neutron in your hand, so if you hold an isolated neutron in your hand, it decays within 11 minutes. It's not there anymore. And that's the reason why the neutron is an unstable particle. And if we were to ask, a little bit more details, it turns out that the force that's responsible for this is called the weak nuclear force, which is different than the strong nuclear force. And so what you're finding here is that what's special about the weak nuclear force here is that it's a process that literally changes the identity of an atom. So when the neutron is inside a nuclei, beta decays literally change the identity of an atom. It literally changes the identity. So then what we should be looking at then is that now that we have this, we need the reaction equation. So the reaction equation, now remember, it's not like we're solving an equation. We're just comparing two sides here. So what happens in the reaction equation? Well, I start with a unstable nuclei, right? And now it's going to go beta decay. Again, this will be in the turquoise region. And you're going to see that there's very specific reasons why this happens. So then I don't change the atomic mass. So if I look at this guy, I'm going to focus on the green. This does not change. Okay, that does not change. What does change is this guy. The atomic number increases by 1. Why? Because I changed a neutron into a proton. So now I have an extra proton. So I decrease the number of neutrons and I increase the number of protons. And then I have a new element here, plus it emits the beta, plus the energy. So when I look at this reaction, what do I actually see here? And these are the important pieces, right? This is important for beta. You see here is that so the first thing I would see here is that the number of neutrons decreases. While the number of protons increases. So protons increase, neutrons decrease. So what this tells us here is it tells us this, that the atomic mass does not change. However, the atomic number value increases by 1. And that's the important piece about this.